Hello and welcome! In this video, we'll walk you through everything you need to know about ISO 3691 guideline for driverless industrial trucks and mobile robots, in simple, clear terms. To meet ISO 3691 safety guidelines, every team plays a specific and important role. The design team focuses on the robot's outer form and user experience. They ensure the robot has safe geometry and human-friendly appearance. The mechanical team works on the robot's physical structure and movement. They ensure safe braking, stability, structural strength, and reliable motion systems. The electronics team ensures all sensors and hardware functions works correctly. They integrate LiDARs, cameras, emergency stops, and communication circuits. The software team brings intelligence and behavior to the robot. They develop navigation algorithms, braking logic, human-aware navigation, and fail-safe responses. Finally, the team lead coordinates all departments to ensure every safety requirement is met. They track compliance, validate tests, maintain documentation, and make sure all ISO standards are maintained. We follow ISO standards to make sure our robots are safe for people and behave in a way that users can trust. These standards guide how the robot should move, stop, and detect obstacles, so it always acts safely and predictably around humans. ISO standards also help us build better and more reliable products. They ensure we meet legal requirements and show that we work professionally and responsibly. Following ISO compliance shows our professionalism, our commitment to building robots that are safe, trustworthy, and aligned with global best practices. ISO 3691 is an international safety standard that defines the requirements for the design, construction, and operation of industrial robot. To meet ISO 3691, we need to cover a set of key safety areas. These include safe movement and navigation, environment and operating conditions, and emergency safety features to make sure the robot can avoid hazards and stop safely when needed. We also need strong sensing and detection, a clear control interface and human-machine interface, and proper battery and charging safety. The standard also focuses on structural and mechanical safety, software and functional safety, along with accurate documentation, labels, and thorough testing and validation before deployment. First, we'll walk through safe movement and navigation for indoor service robots. Safe movement and navigation. It controls speed, braking, path planning, and behavior around humans to prevent collisions and surprise movements. With proper safety logic, the robot avoids collisions, moves comfortably through corridors, handles tight spaces, and interacts safely with people. In indoor spaces, the robot must constantly read its surroundings and adjust its speed. It should move slowly in crowded areas, must stay steady in corridors, and should become faster in open spaces, ranging roughly from 0.3 up to 1.5 meters per second. And if it has to stop, it does so safely. With a controlled deceleration of 1 meters per second square and a reaction time under half a second, it must handle sudden changes without losing stability. Together, smart speed control and reliable braking make the robot move confidently, smoothly, and safely around people. The robot should move with smooth, predictable motion, using S-curve acceleration and wide turns with a radius of at least 0.6 meters, so nothing feels sudden or jerky. As it moves, it continuously scans the environment with LiDAR placed about 200 to 300 millimeters above the floor, detecting obstacles up to 6 meters away, supported by low-level sensors and a safety bumper. And when people enter its space, the robot should become more considerate, maintaining a comfortable 0.5 to 1.5 meter buffer and slowing down the moment someone comes within half a meter. Together, these behaviors make the robot move naturally, navigate safely, and interact with humans in a way that feels calm and intelligent. The robot must make its intentions clear with a 360-degree LED ring that's visible from 3 to 5 meters away and a gentle reverse beep around 65 to 75 decibels so people immediately know when it's backing up. When it does reverse, it must switch into a safer mode, slower mode, moving at roughly 0.3 to 0.5 meters per second. And in tight corridors, it should be less than a meter wide. It should limit its speed even further, making sure it stays controlled, predictable, and safe in confined spaces. Next, we'll walk through environment and operating conditions for indoor service robots. Environment and operating conditions define how the robot must perform in real indoor spaces. floors, slopes, lighting, dust, crowds, and tight corridors. It ensures the robot's design, sensors, and software can handle these variations safely and consistently. Robots must move safely across tile, marble, epoxy, and vinyl floors, even when the surface is smooth or dusty. High-traction rubber wheels with optimized tread patterns and soft, noise-reducing compounds ensure stable, slip-free movement. The robot must maintain full stability and control while operating on indoor ramps ranging from 2 degrees to 10 degrees. An anti-tip, low center of gravity design, torque-controlled braking, downhill speed limit mode, and IMU-based slope detection ensure safe ascent and descent in all conditions. In tight indoor spaces, the robot must stay compact and predictable. Rounded edges, reduced body width, side-mounted sensors, and slow-speed cornering ensure smooth, collision-free movement. In crowded zones, the robot must navigate people safely and confidently. Adaptive crowd-aware navigation, automatic speed reduction, wide LiDAR safety fields, and clear visual or audio cues guide its behavior. The robot must detect and avoid both fixed objects and sudden human movement. Multi-level sensing, real-time path replanning, and slow, cautious approach near obstacles ensure safe navigation at all times. The robot must stay fully functional even in dusty or debris-prone indoor environments. IP54 for dusty environment and IPX2. IPX4 ratings with sealed housings, gasketed sensor windows, dust-resistant LiDAR domes, and smooth, easy clean surfaces prevent contamination and protect sensor performance. In noise-sensitive spaces like hospitals, hotels, and offices, the robot must operate quietly at a decibel level less than 50 to 55. Low-noise motors, rubber wheels, sound-dampened enclosures, and controlled slow acceleration ensure minimal operational noise during movement. Next, we'll walk through emergency safety features for indoor service robots. Emergency safety features are the robot's last layer of protection, ensuring safety even in unexpected situations. This covers emergency stop buttons, fail-safe braking, visual warning indicators, protective bumpers, safe start, restart behavior, fault detection, and audible warning signals. Each system works together to stop the robot instantly, communicate clearly, and prevent uncontrolled movement. The emergency stop button must allow the robot to be halted instantly from any direction. It must follow ISO 13850 requirements, using a large red mushroom-style button with a yellow base. E-stops should be positioned on the front, rear, and top of the robot. Minimum 2 e-stop buttons protected with a shroud to prevent accidental activation and wired through dual-channel circuits to guarantee a fail-safe response every time and horizontally reachable within 1 to 1.2 meter. Fail-safe braking. The robot must stop safely even during power loss or software failure. Spring-applied, electrically released brakes lock by default, supported by redundant brake control, automatic braking during power failure, and slope-holding algorithms. The robot must clearly communicate motion in emergency states. A 360 degrees LED ring with red flash for emergency, and it should be visible from 3-5 meters. Amber for caution or turning, and blue-white for normal operation ensures visibility in all directions. When close-range collisions are unavoidable, the robot must detect impact instantly. Pressure-sensitive bumper strips, micro-switch bumpers, and soft elastomer edges on front and rear zones trigger immediate stop response. They should have a low impact force of less than 50 Newton. After an emergency stop or restart, the robot must remain stationary until safety is confirmed. A 2-step reset, safe to start checklist, visual countdown, and audible confirmation ensure controlled and intentional restart. The robot must enter a safe state, slow or stop when any fault occurs. Watchdog monitors, redundant sensor health checks, auto stop on LiDAR disconnection, and clear LED plus screen error alerts maintain operational safety. The robot must warn nearby people with clear audible cues. Reversing beepers, voice prompts like robot reversing at a decibel level of 65-75. Next, we'll walk through sensing and detection for indoor service robots. Sensing and detection are the robot's eyes and awareness system, everything it depends on to see the world and react safely. In this section, we'll cover the 7 key elements. Multi-level obstacle detection, 360 degrees protective field coverage, human detection and interaction safety, redundancy for critical sensors, sensor protection and cleanliness, close-range contact detection, and sensor-aware form design. The LiDAR plane must be mounted between 100 and 300 mm above the floor. Floor-level time-of-flight sensors should detect obstacles as low as 0 to 150 millimeter, ensuring even small items are captured. Mid-range ultrasonic IR or depth cameras must cover the 200 to 600 millimeter zone to detect legs, stools, or bags. These height layers together ensure no obstacle is ever missed. The robot must maintain complete 360-degree protection with 0 blind spots. Dual LiDAR, one in the front and one in the rear, should be used to guarantee uninterrupted coverage. The enclosure must not block any sensor field of view, and every side, front, rear, and lateral should be monitored at all times. The robot must maintain a personal space buffer of 0.5 to 1.5 meters, dynamically adjusting based on the environment. Human detection should use safety-rated scanners meeting PLD or SIL2 where required. These layers ensure the robot behaves respectfully and predictably around people. All critical safety sensors must have 2 independent sensing modalities. There can be no single point of failure. The system should detect faults within 100 to 200 milliseconds, immediately entering a safe state. This redundancy guarantees consistent safety under all conditions. Sensor windows and domes should use anti-glare and anti-scratch coatings to maintain clarity. All sensor housings must include gaskets rated IPX2 to IPX4, protecting the system from dust, smudges, and moisture. Clean, protected sensors ensure accurate performance at all times. A physical bumper must activate at forces below 50 newtons, triggering an instant stop when near-field sensing cannot detect an obstacle. This provides the final safety layer for unexpected contact. The robot's exterior must avoid glossy or reflective surfaces around sensors, especially in the LiDAR plane. Matte finishes should be used, and the form must include smooth chamfers with no protrusions blocking the field of view. Good form design ensures clean and accurate sensor readings. Next, we'll walk through control interface and human-machine interaction for indoor service robots. A safe indoor robot depends not just on sensors, but on how people interact with it. That's why the control interface and human-machine interaction must make every command, alert, and override clear and intuitive. In this section, we'll cover how the robot communicates through mode indicators, a simple touchscreen UI, manual override, and ergonomic controls, along with audio cues, visual intent signals, and a service-friendly interface that keeps operation easy, reliable, and safe. The robot must always make its operating mode instantly recognizable. No guesses, no confusion. LED indicators should follow strict color coding: green for auto, blue for idle, amber for caution, and red for error. A clear mode label must be shown on the HMI screen at all times. And to ensure visibility from every angle, a 360-degree indicator ring should display the robot's current state across the entire workspace. Users must know exactly what the robot is doing before they even approach it. The robot's touchscreen interface must be simple, readable, and accessible to every user. It should use a 5 to 7-inch display, large high-contrast fonts, clear icons, and a glove-friendly touch response to ensure operation in all environments. For maintenance or repositioning, the robot must support safe manual override. Manual mode should only activate through a key switch, with a dedicated joystick or push handle and a motor disengage button for safe towing. All buttons and interaction points must be ergonomically placed. Controls should sit between 900 to 1200 millimeter in height, with recessed or protected housings and illuminated buttons for low-light areas. The robot must provide unmistakable sound cues, soft startup tones, reverse beepers, voice prompts like robot turning for around 0.5 to 1 second, and adjustable volume modes of decibel level around 65 to 75 for night or hospital use. The robot must clearly show its movement intentions using directional LED arrows, floor path projection lights, and pre-movement scanning animations to indicate turning, reversing, or docking actions. The service interface must support fast diagnosis with a dedicated technician menu, QR codes linking to manuals, and on-screen error descriptions with detailed logs. Next, we'll walk through battery and charging safety for indoor service robots. Battery and charging safety is crucial for protecting the robot and its environment from electrical and thermal risks. In this section, we'll cover the 7 key pillars: battery thermal management, safe battery enclosure and positioning, secure electrical isolation, safe auto-docking and charging alignment, charging safety and overcurrent protection, battery health monitoring and alerts, and safety during manual battery service. The battery system must stay within safe temperatures at all times. Charging must occur between 0 to 40 degrees Celsius, storage between -20 to 45 degrees Celsius, and the system should trigger lockout if temperatures reach 60 degrees Celsius or above. Every module or cell group must include temperature sensors to ensure early detection of overheating. The battery must be enclosed in a fire-resistant housing, metal or FR-rated polycarbonate, with a minimum protection of IP20. It should be mounted low in the chassis to maintain a low center of gravity, and must be supported using shock-absorbing mounts to withstand impacts. All high-voltage connectors must remain fully insulated. Any charging contact above 60 VDC requires additional safety measures. The robot must use power cut relays, fuses, and residual current detection to isolate electrical faults instantly. The robot must approach the docking station slowly, no faster than 0.2 to 0.3 meters per second during the final 0.5 to 1 meters. Docking must tolerate misalignments of approx 5 to 15 mm, supported by mechanical guides or magnetic connectors. The BMS must actively prevent overcurrent, overvoltage, overheating, and ensure cell balancing. The system must perform a hard cut if temperature reaches 60 degrees Celsius or if current exceeds the fuse rating. The robot must continuously log cell voltages, temperatures, and cycle counts. It should return to dock when the battery drops to 20 to 30% SOC, or when the state of health declines beyond the safe threshold. Battery service must be safe and controlled. Access panels should be toolless but lockable, and all service handles must be insulated to protect technicians. Next, we'll walk through structural and mechanical safety for indoor service robots. Structural and mechanical safety ensures the robot's physical design is strong, stable, and safe for anyone around it. In this section, we'll look at 7 key elements: rounded edges and safe geometry, anti-tip stability, impact protection and robust body panels, safe wheel and drive system protection, secure load support and payload stability, structural integrity for indoor obstacles, and safe and accessible maintenance design. Rounded edges and safe geometry must be maintained across the robot. All human-reachable edges should have in radius 4 to 10 mm, with radius 6 to 10 mm preferred in areas with frequent contact. Soft foam or elastomer bumper trims must surround the perimeter to minimize impact risk. Anti-tip stability must be ensured by keeping the center of gravity low using battery and heavy components mounted at the bottom. The wheelbase should be wider than the height to maintain balance, and the robot must safely support up to 5 degrees slopes, with validation up to 8 to 10 degrees when required. Impact protection and robust body panels must rely on high-impact materials. Panels should use ABS PC blends or metal, supported by foam-backed and replaceable bumper skins. Corners must be protected using rubber or TPU guards to absorb shocks. Safe wheel and drive system protection must fully enclose the wheels and drivetrain. There must be no pinch gaps where a 12 mm probe could enter. Ground clearance should stay above 20 to 25 mm to prevent objects from getting trapped underneath. Secure load support and payload stability must keep items steady during movement. Trays should have anti-slip mats and raised lips of 10 to 20 mm. Mechanical locks should be used for loose or tall items to prevent tipping or sliding. Structural integrity for indoor obstacles must be reinforced using internal shock mounts for electronics, thick front bumpers, and sacrificial skid plates. High-impact polymer housings must protect vulnerable sensor zones. Safe and accessible maintenance design must allow easy servicing without compromising safety. Access panels should be toolless, but include safety interlocks that cut high voltage and motors when opened. Critical covers must use captive screws or tamper-proof fasteners. Next, we'll walk through software and functional safety for indoor service robots. Software and functional safety ensures the robot behaves predictably, even in unexpected conditions. In this section, we'll cover the 7 key pillars: fail-safe behavior, redundant safety monitoring, watchdog timers, error detection, predictable motion control, controlled restart, and safety for remote and manual control modes. Fail-safe behavior must guarantee that the robot slows, stops, and locks safely during any fault. The system should follow a staged, slow, stop-brake sequence, achieving around 1 meter per second square deceleration, and when a critical fault occurs, it must drop to less than 0.3 meter per second before performing a full stop. Redundant safety monitoring must eliminate single points of failure. Critical detection should use dual modalities, such as safety LiDAR plus 3D vision, or dual LiDAR channels, supported by redundant IMUs or dual odometry checks. Watchdog timers must supervise every critical control module. Heartbeats should update within 100 to 200 millisecond, and on any watchdog trigger, the robot must cut drive power and engage brakes in under 200 millisecond whenever possible. Error detection must be fast, traceable, and remotely visible. Event logs must use synchronized UTC timestamps with at least 10 minutes of circular history, and critical events should be pushed to the fleet manager within 30 seconds. Predictable motion and navigation control must ensure smooth, human-safe movement. Motion profiles should use S-curves with jerk limits between 1-2 meter per second cube, reduce sway under payload, and strictly enforce zone-based speed limits. Controlled restart must prevent unintended movement. After power-up or e-stop release, the robot must never auto-drive. Motors should only enable after user confirmation, followed by a self-test and a 3 to 5 second visual countdown. Safety for remote and manual control modes must enforce strict access and speed limits. Activation should require a key switch or authenticated token, and all manual or remote movements must be capped to less than 0.5 meter per second. Next, we'll walk through documentation and labels for indoor service robots. Documentation and labels ensure every user, whether an operator, technician, or safety inspector, can clearly understand the robot's safety information. In this section, we'll cover the 7 essentials: clear safety labels, operating instructions, emergency procedure info, maintenance and service documentation, compliance and certification labels, charging and battery labels, and mode indicators and HMI status. First, let's talk about clear safety labels on the robot body. These must follow strict visibility and ISO standards. All labels should use mandatory ISO 7010 pictograms, no exceptions. They must be sized for readability, at least 15 mm per meter of viewing distance, and crucially, they must be placed directly next to the hazard at eye or hand level, specifically between 0.9 to 1.5 meters. Operating instructions for users must be simple and fast to understand. The HMI should show 3 to 5 pictogram steps, supported by a QR code of at least 20 by 20 mm, with on-screen text readable at 0.5 to 1 meter using 14 to 16 point fonts. Emergency procedure info must be unmistakable. All e-stops should have ISO 7010 emergency stop icons with directional arrows and red markings. Labels must be readable from 1 meter, following the 5 mm uppercase rule, and the HMI should display a 2 to 3 step emergency pop-up. Maintenance and service documentation must be accessible and technician-friendly. The robot should include a PDF service manual plus a printed quick service sheet inside the maintenance bay, along with exploded diagrams showing fasteners and torque values. Compliance and certification labels must be durable and permanent. A metal or long life sticker should list the product name, model, serial number, year, payload, electrical ratings, and compliance marks, placed prominently on the rear panel and near the battery access. Charging and battery labels must guide safe docking and warn users of electrical hazards. Docking areas should have alignment arrows labeled "Align here," while battery warnings like "Do not touch while charging" must follow viewing rules. Readable from 0.5 to 1 meter using 5 mm uppercase text. Mode indicators and HMI status must be visible, clear, and unmissable. A 360 degrees LED ring and HMI icon must show the active mode from 3 to 5 meters, while audio alerts must play during errors. The HMI should display mode text icons readable at 0.5 to 1 meter. At the end, we have testing and validation for indoor service robots. Testing and validation ensures the robot meets ISO 3691 safety requirements and performs reliably in real-world environments. In this section, we'll cover the 7 key areas: movement and braking performance, obstacle detection and safety, field validation, stability and structural durability, battery and charging validation, software failsafe and recovery, usability and HMI testing, and endurance stress and cycle tests. Movement and braking performance must guarantee reliable stopping across all floor types and payloads. The system should use a design deceleration of 1.0 m/s2, maintain an emergency stop latency under 200 ms, and meet calculated stopping distance requirements with at least a 20% safety margin. Obstacle detection and safety field validation must ensure the robot detects hazards early and stops before contact. Warning fields should cover 2-6 meters, protective zones 0.3 to 1.0 meters, and the robot must detect low obstacles of 0.50 mm at operational speed. Stability and structural durability must prevent tipping and ensure long-term strength. The robot should withstand slopes of 5 degrees, tested up to 8 to 10 degrees, endure 500 to 1,000 impact cycles, and secure payloads so none shift or fall during max speed turns. Battery and charging validation must confirm safe docking, thermal control, and long-term charging reliability. The final docking approach must be less than 0.2 to 0.3 meters second in the last 0.5 to 1 m, with alignment tolerance of approx 5 to 15 mm, and the BMS should cut out at more than 60 degrees Celsius. Software failsafe and recovery must bring the robot to a safe state during crashes or sensor failures. Watchdog checks must trigger within 100-200 ms. Transitions must slow the robot to ATO 3 m per s before stopping, and no movement should restart without manual confirmation. Usability and HMI testing must ensure operators instantly understand warnings and actions. Text must be readable from 0.5 to 1 meter with 14 to 16-point fonts, 360 degrees. LEDs must remain visible from 3 to 5 meters, and audio alerts must reach 65 to 75 decibel at 1 meter. Endurance, stress, and cycle tests must verify long-term reliability. The robot should complete 24 to 72 hours of continuous navigation, withstand 500 to 2,000 docking cycles, and pass thermal cycling from -20 degrees Celsius to 50 degrees Celsius, plus vibration testing per IEC profiles. To meet ISO 3691, we must design robots that move safely, sense reliably, and act predictably around people. We need controlled motion, strong obstacle detection, clear human-aware behavior, and robust, stable hardware. Our software must include real fail-safes and controlled restarts, and every system must be validated through rigorous testing. Together, these steps bring us closer to safe, trusted, ISO-compliant robots. By following all 10 pillars, from safe movement to testing, we move closer to full ISO 3691 compliance and a safer, more predictable robot. Thank you for your time. Let's continue building robots that people can trust.